Welcome to my recording on roofing. We're going to go through drawing 2018-06. I'm just going to break down the description in a way it appears on plan, and that is about it. I'm not going to give you any more information than that. Just joking, I will try and explain as much as I can. Okay, we're going to start with plates. We're basically describing what exactly the truss or roofing construction is going to sit on. In contact 1, we were told it's an uneven brick surface and we need to apply a wall plate. So there's your timber wall plate, it's a standard description. We'll get to the coating. Let's just cover this. 2 times 26.5 and 2 times 10.9. Let's go across the drawing. So there's 26.5. Now, it's quite clear that that is one of the 26.5s, okay? But why 2? And the reason it's 2 is because we have simplified that other side and we've made it equal. And the 10.9, if we were to look on this face, at wall plates specifically, these individual lines indicate trusses, but we do not have any trusses resting on these exposed brick areas. That's because that's a parapet wall that is on those gable ends, and there are no trusses that rest on the gable ends. So the 10.9 does not extend that full length, and you'll find it there. 10.9, 26.5, 26.5 there, and 10.9 on this side. Okay, so I think that is pretty self-explanatory. I'm going to go ahead and raise everything quickly. So that would be wall plates. Standard description for wall plates. I'm not sure if it ever changes. I really doubt that. We'll go over to the coating. Okay, 0.3. I'm sure you should know this by now. If you take the dimensions of your wall plate, 2 times 38, 2 times 114, it'll come to something roughly 0.30. I think it might be 0.304 if I'm not mistaken. Oh, here it is there. It is done for you. Well, not done for you, but that is how you come to that calculation. Basically, it's a perimeter calculation. And you do not coat the ends because that is ridiculous. It's not ridiculous. You do coat them in real life, but you don't measure it. Don't ask me why not. Okay, down to full trusses. 34 full trusses. Basically, this is done by just counting the blue lines on plan. It is not rocket science. I think you should be able to do it. What we've been told is that this little one there, and that little one there, should be considered a full truss. So I just said it's 2, but actually there are 3. 1, 2, and even this one. 3 full trusses on the inside. And then you're going to count these individual ones all along. Sorry, not that far, up to there. And you'll get 34 full trusses, okay? Raise this quick. So 34 full trusses. 7.38 is the dimension for our tie beam, right? Let's take a look here where 7.38 came from. It was, and let's just go back here. Okay, it's not explained, but it was 7.6. Let's just drop it down here. There we go. So we've taken this dimension, 7.6. We've subtracted. You'll notice where it starts and ends. Sorry, the side is a bit messy. Nope, made it worse. Okay, it starts and ends on the inside face of the outer skin. I know it's confusing to understand. So you've gone from the outer edge and you're going 1 brick thickness inwards, and that is it. So we've subtracted 2 times 110, and you will get to 380. Okay, that's where that measurement comes from. So we are saying that the tie beam covers the inside span plus the brick and the cavity. Okay, brick and cavity on both sides. And if you're going from the outside, it's only 1 brick in and 1 brick in, and that's it. Okay, so there's 2 ways to measure this. You should probably take note because I know it will be asked in as many different ways as possible to try and test your flexible thinking. So inside out or outside in, just remember there are different ways of measuring it. Okay. Let's jump back to measurement. Okay, so I gave you that calculation. You've got your description. Just remember that to add that in. What I usually do is, since you're not sure what this number is, because I usually start with the description and then I write up to here at this point, exceeding. And then if you're not sure, you do your calculation, you realize, okay, it's exceeding 6.6, so you throw in 6.6 there, okay? If it's exceeding 2.4, you throw in 2.4. And then you realize, okay, because it's over 2.4, it cannot be exceeding, when the next category is 3.9, right? Okay. On to our rafters. Okay, rafters. So rafters is broken down into, there are 2 rafters per truss, right? And there are 34 trusses. Okay, 5.74, where does that come from? So I see there's a note here that says the length is scaled. So we can assume that what's happened here is that this length was scaled for the rafter, the screen. Okay, that was scaled with a ruler using 1 to 25. Okay, that is pretty self-explanatory as well. Just remember your description. It happens to be in this example the same timber as what we have in our our wall plate. It's not always the same. Okay, so maybe I should just go over this. Is 2 per truss, 34 trusses. Obviously, 1 on that side, 1 on that side. You apply it to your previously counted 34, and then you have your dimension, your description completed. Okay, 1.87 meter strut. Okay, again, this is in scale, so we'll go over to this one. So in the event that you're not given any of these dimensions, right, you'll just be given a diagram of the truss and a section scale. You'll take your ruler and you'll take it to the furthest point, as indicated here. So including this little, I don't want to call it, it's like the shaped end. Including the shaped end, you take it past right to the corner, and then with your ruler you measure right to that corner as well. Okay, so in this case for the strut, what she's done, since we're doing the shorter strut at the moment, she's gone to this furthest point, which is that corner, and she's gone to this furthest point, which is that corner, right? Okay, she's used the ruler, converted it to millimeters, and came out to 1.87, 1,870 millimeters. Okay, so that means, and let's just reverse engineer this. If this is 1,870 on a 1 to 25 scale, that means that this real distance on paper, this real measurement on paper, is 1865. Now it's divided by 24, right? And you'll get what she measured with the ruler. Okay? Same theory, just working backwards. There we go. Clean up a bit. Okay. Cool. Okay, we're going to move on to the longest strut. Longest strut applied the same theory. She's taken a scaled length. So she measured on paper with the ruler and times it by 25. Okay, because it's 1 to 25. So sorry, it's not actually this that's times by 25. It's what was on paper that's times by 25. So this 3,270 is actually divided by 25 to get back to what she measured on paper. Okay, anyway, I digress. There are 2 per truss and there are 34 trusses. And that covers your long strut. Over to a collar, which is something new. And the same applies with the scaling. Just done long strut, done the short strut. Here's your collar. Now, the collar is not so obviously indicated because of the dotted lines and solid lines. So, what you do, I assume either it'll be indicated there or in your spec that there's a collar. And you should know that when they say there's a collar, there's something holding struts to the apex of the truss. So, struts all come together with the rafter and meet at the collar. And I'm not actually entirely sure how we would figure out the size of the collar. I guess we just assume it's the top of the strut. Oh, we wouldn't need it. Let's just take a look here quick. So for the collar, I think what we only need would be that one, 152. So this is 152, right? 152. And then the length will be scale, as she said, scale, which is furthest point to furthest point, corner to corner. The reason they say they measure from furthest point to furthest point is because it is still a long piece of timber that had to be cut, right? Corners had to be cut off. But what do you do with these corner pieces now? Pretty much nothing. Okay, throw it away. Construction waste. And it can't be the short end because how would you cut a smaller piece to make a collar when it's supposed to be this big? You wouldn't be able to make it. Well, I guess you could if you were creative, but it's not efficient use of time, not at all. Anyway, that is an explanation of why to scale from furthest point to furthest point. Extra information. Anyway, let's back it up a bit. Back to drawing. Come on. Okay, we're going to go over to hoop iron. Hoop iron is also pretty self-explanatory. You are going to have your trusses resting on your wall plates. Let's go down here. You see in this drawing, actually, the wall plates have been indicated. And the only thing holding these trusses down, other than their own self-weight, their own dead weight, is the hoop iron that we're going to add now. So I'm not exactly sure, but one end goes in that side. I'm not sure if it goes. It might go over both the tie beam and the rafter, and I don't know how many times I loop it, but it's long, 1.5 meters long. One end fixed to brickwork, one end fixed to timber. Basically, I stand under correction, but whilst it's enough weight to hold itself down, negative pressure from winds does create some sort of lift that wants to sort of pull the roof right off the wall. So obviously you do need to fix it down to your structure, okay? I don't know the details, you're going to have to figure it out yourself. or ask a lecturer. So that's that. roof ties, timber steel connectors. Not exactly obvious every time. Let's see how this one comes out. So it's 3 per truss, there's 34 trusses. Okay, so 1, 2, 3. Okay, so you can see clearly that in the absence of any connectors, we have to assume they're fixed somehow. And in the diagram, if there's no dot, there's a dot. Dot would be bolt. No dot is, we'll call nail plate. Okay? In the absence of any visual indication, we have to assume that there's a nail plate there. Something has to be holding those pieces together, and it's a nail plate. I would argue that this one's not so obvious because we already have a collar there. So to put a nail plate here, yeah, anyway, it's extra. Let's call it extra. Whilst we're here, let's go over the bolts. So I've just said in the absence of any indication, we assume it's a nail plate. In the presence of dots, it is a bolt. I say a bolt very specifically because it's not the bolt. There are types of bolts, M16 and M10, and that pertains to the thickness of the timber it has to travel through, right? So 100 mils plus is a M16. Now I don't mean the weapon. And an M10, we will just assume it's less than 100 mils. Okay? This is because I'm being a bit lazy and not looking at the table. There is a table for these bolts. Let's just make things a little bit easier. Okay, so 100 mils or less is M10, and greater than 100 mils we'll say is M16. Since we know that this one, thickness is 38, this one coming in here, thickness is also 38. Okay, let's take a look at this one. I forget what the tie beam was it 52? I think it was 52. It was also 38. Okay, 38 tie beam, 38, 38. Okay, so let's just analyze 2 intersections. We'll take a classic example of these two experiencing the same amount of members that they need to connect, right? We've got three intersections, and that's the same as the side. Okay, you've got to make sure it's the same. So we're going to group them together. 3 by 38. Okay, and the rule is you're going to take the thicknesses and 2 times the bolt's diameter. So since this is already 38, so it's over 100, we'll say this is M16, okay, because it's over 100. So we'll do 2 times 16 instantly. 2 times the bolt diameter, and that will give you what's going on here. So this is a calculation I'm busy doing. 3 times 38, and this is 2 times 16. Oof, just squeeze it in. Okay. This gives us a total bolt length of 146, which we round up. 150 mil bolt length, okay? There. 150 mil bolt length. And we are saying there's 2 per truss. Let's jump back here. 2 per truss is this, what I've just done here. And it's M16, like I said previously, because it's over 100 mils. Okay, we've got to go back to our M10. Now the M10, this is 2 times 38, right? That is 2 times 10. So from, it's actually not always so obvious, but what we say here is that since that is only 76, we will get away with using an M10 bolt, because it's under 100, right? If we use an M10. It's only 2 pieces it has to go through, we'll apply M10. If it's 3 pieces and it's over 100, like here, we apply M16. Okay? So, description is 6 per truss. We'll go back over to the truss. Let me change colours, that's a bit obvious, so I look like a mess. I apologise. It's usual. 1, I can't see yellow. 2, 3, 4, 5, 6. Okay, 6 per truss. 34 trusses again, we just carry through this 34 all the way. Keeps going. Okay. Split rings, there's a rule that we're applying here. The first rule is that there are 2 split rings per M16. Okay? 1 split ring per M10. Okay? Same. Okay, we're saying there's 2 per truss. And there are 2 split rings per M16, and there are 34 trusses. Okay. And we've taken this one, M10. We're saying there's 6 per truss and 34 trusses. Okay, it's pretty straightforward, I think. Moving over to our half trusses, so let's just take a look at the drawing so we understand properly what's going on with the half trusses. Okay, so a half truss is very nicely indicated as pink on the drawing. I don't think it'll always be so obvious, so just be careful. Basically, here's a bunch of half trusses. Here's one here. Okay. So you're going to count them, and you'll come to 10 half trusses. Great. So, tie beam might be easier to take a look here. Here's our tie beam. 3.69. So we've been given a half truss diagram, drawing, and it's given. It doesn't even say scaled, so we might say scaled on. No, it's not scaled. Okay, just given. 3.69 is given. Exceeding 2.4, not exceeding 2.9. That's a standard, straightforward description. Don't need to explain that. This says scaled, and it's 5.74. Let's take a look. So 5.74 is the same, right, as the full truss. I would not risk saying it's the same every time, but in this case it is the same. It's the same scale dimension, so it's the same. It's scaled. There are 10. You just applied. Now the trick here, obviously, is a half truss, not a full truss. So in the full truss, what we did was we said one raft is this length. There are 2 in a full truss, and there are 34 full trusses, right? But since it's a half truss only has one side. Okay, obvious. But I get the feeling this is something I would get wrong because you're doing things so fast in assessment environments. You just end up putting 2. In fact, that's something I would do. Bet you. Anyway, short strat, scaled, straightforward. They're the same from this one, 1.865. Yeah, so it's exactly the same as the full truss. What has happened here? Let's just take a look. 1.865, 3.338, 3. That's interesting. The longer strut, slightly different, guys. See that? 3.338, 3.268. Okay, interesting. But the shorter strut is the same. Okay, so let's not use the full truss. And I think we could. What's happened is that it's gone a bit. 3.338, 3.268. It's gone a bit further at the top. I think must be at the top, right? So this point at the top where it was scaled is a bit longer than the full truss point where it gets scaled. Tiny bit, anyway. And what you also notice, which will come up just now, is that we have had to add a king post because basically there'll be nothing holding up this top section. So this king post is going to hold up our rafter, which basically wants to collapse like this. I mean, sure, we have some struts, but it's not enough. Anyway, short strut is pretty straightforward. That's given, well, not given, scaled. Move on to long strut and king post. I'll just explain the king post. There's something to look out for here. Is that, let's say we're not given this, and we're told that we have full trusses, and maybe we're just given this. We will have to decide that we need a king post, right? It's not so obvious in my opinion. There's something that can be easily overlooked. Okay, you need to remember to add a king post when you're doing half truss. Okay, and the length of that king post in this example is 3225. Let's just take a look if that was also scaled. So it was scaled. So what happened is, let's just go here. If you are given a diagram, you can simply scale, and that's fine. If you do not get a diagram, you go over to your your full truss, and you're going to decide, come on, there we go. You're going to decide, I'm going to put king strut here. I just need to take a look. Where exactly does it start and end? It's very interesting. It goes straight to the top, guys. So, back it up again. It actually is a little bit shaped at the top. It's flat. And when it comes to the top, it's going to make a point. Okay, and then all of this does not exist. Now we've just designed a half strut. If it's not given, we've designed a half truss if it's not given. And we would scale this. It comes out to 3225. Okay, that's in the case that it's not given. And it will fall into this category, 2.4 and not exceed 3.9. So that is the next category after 2.4. You can't throw all of your struts in the same place. They have to be appropriately spaced out. So the first one would be less than 2.4, right? Then we have 2.4 to 3.9, and then 3.9 to 6.6. Okay, you've got to apply them into their correct categories. Otherwise, you're not using the right rules for your standard system. These categories are important. Don't ask me why. So 10 is how many half trusses we decide there are on plan, and these two we've covered as scaled from this diagram. Okay, if this is not given, I would suggest you follow this route, or you're going to lose a mark for not putting in your king post. You might lose more. Sorry, king strut. It's also called the king post, I think. Go down. Hoop-iron. This one is interesting and quite logical, which is why I enjoy it. We will take a look. You are putting hoop-iron on a half truss. So a half truss only has bearing on the wall plate once, because it's half. Okay, it's pretty obvious. But if you're going fast in an assessment environment, you could overlook it and just put 2 per half truss. It's 1. Why? The other side is actually bearing down on what we're going to put in later, which is a ridge beam. Okay, and the tie beam, I'm not actually sure what happened in the tie beam. We have a half truss, Basically, that's what a half truss looks like. If you're looking from a cross section. I'm not going to draw the struts. Okay, so your hoop line is going over here, and this is meeting at a ridge beam. Okay, I'm not sure how to draw it, but I'm not sure what happens with our tie beam over here. We have our king strut sort of holding it there, and on this side we've got a couple of jack rafters coming across. Now the jack rafters are coming from an angle. It's pretty tricky to draw, so you won't be able to see it. Anyway, they're coming to the top of the jack rafters. They're not going to the bottom. So what I would like you to think about, and I don't have an answer for, is what is connecting here. You walk into whatever building this is, looks like a house, and basically it looks like you have a bunch of full trusses, right, and tie beams. Suddenly you have, so let's say the full trusses run like this, in front of your half trusses, a bunch of full trusses and tie beams. Suddenly you have no full trusses and a half truss, a couple of half trusses, and I think there'd be nothing here. There'd be a big void over here in terms of our truss. Our truss network would be pretty empty, and then we'd return back to full trusses down here, right? Bunch of full trusses and full tie beams, full length tie beams, put it that way. This is a half length tie beam. So void over here in your tie beams, there's no void in terms of your jack rafters. These are all jack rafters. So the top of the roof still has to be supported, obviously, for our battens to fix onto, but there's a gap underneath here where there's no tie beams that don't extend. Anyway, thought of the day, you just figure out how the ceiling is going to be fixed, or what ceiling could be used. I don't know, maybe it's an exposed roof system. Look into the trusses. I'm not sure. Maybe we just don't measure it, but there's something that goes there. Let's clean up a bit. Okay, let's hop back onto double steel connectors. Standard. So what I do is, the only thing I struggle to remember is this one is 1.6, right? This one, 1.2. So the hoop line is 0.4 millimeters thicker. That's the only sort of tricky part to remember there. The rest I find relatively easy to remember. 1.5 meters long. So we used AB as before because it's already been described, and it didn't say blah blah blah. One end fixed it to brickwork and the other end fixed it to timber, because that's unnecessary repetition, and we need to eliminate that, especially in these assessment environments where time is short. So go down to bolts. I want to say that it's half, but it's not. It's not half because our king post has changed things, right? So we can't make assumptions about our M10 number. It's not half. When you look at our diagram, if you've drawn your own diagram, you'd have to say, well, I've added a king post here, and since I'm the designer of my half truss, I say there's a bolt there, and maybe, let's see what it is. Okay, and I say that this one moves there, and this one moves there. If it's not given. If it is given, well, obviously just count. Double connection, oh, sorry, two thicknesses, two thicknesses, two thicknesses, two thicknesses, right? There are 4 versions of the 2x38. And since this is well under 100, we're going to say it's M10, 2 times 10, and that's 96, which would make 100 mil. That's a 100 mil long bolt, M10. There are 4 there. Let's go back. 100 mils, 4 per half truss, and a 10 half truss on the drawing, as indicated. And M16, we'll do the same. The last bolt left in this diagram, remember, this is still, have we done nail plates? I brushed over it, I'll come back to it. Let's finish our M16 though for now. So, M16, the only M16 here is this one, 3x38 and 2x16, because this number is over 100 already. Okay? And there's only 1 per half truss, and there's 10 total. Here's our 140, this is 3x38, 2x16. I'm not exactly what that exact number is, but it will not be exactly 140, we round it up or down to 140. We'll go back to the nail plates, the steel timber connectors. We've said there are 10, let's take a look here quick. So, as I previously said, in the absence of an indication as to what is connecting the members, we assume it's a nail plate. Okay? Bolts everywhere else, because there's your dots. But there's a nail plate here, 100 by 150, 1.2 millimeters. Told you, I forget this, 1.2 millimeters. Anyway, same rule here. Okay, 2 for M16. So since we said there's 1 M16 bolt, what's happened here is a bit of a shortcut. It didn't really explain. So what I would have done is I would have said it's 10 half trusses, there are 2 split rings per M16, and there's 1 M16 bolt. That's probably how I would have described it. And if we go over to the M10, M10 is simply 1, 2, 3, 4 M10s. So again, I would have expanded this a bit more to make it more obvious to me, because that's the most important part when you're describing and measuring, is that it must make sense to you. Otherwise you're going to forget or write down incorrect measurements. So there's 10 half trusses, there's 1 split ring per M10, and there are 4 M10s. So basically I'm expanding this measurement, this collection, to make sense to me in my mind. I'm saying 4 bolts, for an M10 is only 1 per bolt, and it's 10 half trusses. Okay, easy. Same story for M16. 1 M16, 2 split rings per M16, there's 10 half trusses. Okay, this 2 take is everywhere where we've left out, and it kind of touches on what I was saying here, is that we have a bunch of half trusses sort of floating in the air here. But how do we fix the half truss where it meets, let's say where it meets jack rafters, or where this one meets the top here? We haven't counted for fixing this end onto the main roof structure. So this end onto this roof structure is not accounted for, and I think the same goes for whatever happens at the bottom, the tie beams. What are we attaching our half tie beams to come across? We have not taken them. And as I said previously, I'm not sure if there's anything down here. It could just be open space. Oh, my word. Okay. Let's go over to hip rafters, valley rafters and jack rafters. Okay, we're doing the last of the rafters, these sort of tricky, odd ones out. You know, they're not so straightforward. This is where a bit of the math comes into play. You have to understand what's going on. Okay, so I'm going to break it down into. Well, let me go across here and explain. The way I see it, let's say we want this. And I know this is a bit of a sticking point in MDA1, because it is tricky, I will be honest, I had to wrap my head around it. So we're saying, and by the way, this is actually what I write down when I do the calculation, is this square here, I'm taking it out, and I'm going to use it to calculate. And what am I calculating? Well, firstly there's x, and this is x there, and this is y on the side, okay? So x would be the slope of the roof as it runs up. So from the side view of our square, this is x. Okay, y is a whole other story, we'll get to it. But from the side view, as you're looking into this building, x is on the slope. You first need to find this x, okay? If a factor for x, or the actual value for x, you can decide. We say for 1 unit here, what would x equal? So let's bounce back, we need to find out what the pitch of the roof, 40 degrees. Okay, there it is. So it's given as 40 degrees. And from here, it's pretty basic trick, but you need to keep track of what you're calculating. So we're currently doing x leading up to the apex in a straight line, so perpendicular. Right? Perpendicular to our ridge. First. Okay. Use cos. And from high school, adjacent over hypotenuse. Do some rearranging. Okay, so adjacent was 1. So what it ends up being is 1 over cos 40, and if we jump across to here, we'll see that this is a factor 1.305 per meter, because 1 divided by cos 40, yes, it's exactly the same as what I've done. 1 divided by cos 40 gives us a factor, let's call it a ratio. For every 1 unit this way, we get a 1 point, things are getting a bit messy here. For every 1 unit we travel that way, we're getting 1.305. 1.305 units on the top. Okay, this doesn't help fully, because we're trying to get this one, which is our hip rafter, and this one's our valley rafter. We must deduce that because this one's on the end, it must be a hip rafter, because, well, it's pretty obvious it's a hip rafter, okay? It's coming from a higher point here, and a higher point here. Okay, so it could be going down, but that'd be a very weird roof. Anyway, it's a hip rafter. This is a valley. I'm trying to think how it actually. So when I would say, here's the proof that it's a valley. When there's an intersection that's shaped like a T, let's say, it can only be a valley. Okay? Because this is a ridge that's higher. This side's also higher. This line can only be down. And we're coming from one side that's higher on this side. And that's it, just one side. And this one sort of, so what I'm trying to explain is sort of, how do we decide, and I'm getting a bit sidetracked, but how do we decide it's a valley or a hip? But let's just go back to what we were doing. For every 1 unit across, we've got 1.3 that travels up along the slope. Okay? But we still haven't gotten our y. This is our x, by the way, 1.305. This is 2D. Yeah, so basically squares is 2D on plan, but this is actually raised. Y is raised because it's on the hip. You know, it's really tricky to draw it. I'm not sure if I can draw it without embarrassing myself. But let's just say it's kind of, so yeah, I guess this kind of makes sense. So 1.3 is here. We don't know what y is, and this side's also 1.3. So we divide this into triangles now. So what we've just done is applied some trig to get to 1.3, and then we're going to apply Pythagoras to get to our actual rafter length. So we come across to a triangle, right? This is basically two triangles, and what I tried to draw earlier, which I didn't do very well. It's not a perfect square when considering the three-dimensional shape of it, right? Only on plan is it a three-dimensional square. I mean, yeah, two-dimensional square. Once we've turned it into a triangle, we're going to take, if we remember, we've taken half, come across here. So in this example, that was already converted. I'm still working with, let's say, a factor. And maybe I could take the factor all the way, and then we get a factor here. But for the sake of the example, let's convert this. And when we convert it, we're timesing this by our factor on slope. So something interesting that is worth noting, guys. This was not taken, which is odd because we could have. What happened instead was we got the factor, which I've shown you, but we divided by that. 8,650 divided by 2 to get half. Okay. Here's our 8,650. So dividing that by half gives you that. The only question left is, what is this total length? Now, what I said previously is that it's interesting we didn't take that, and instead we calculated that it is half of the full length. And the reason being, no, I still can't explain why this wasn't taken. I do not know why this rafter length was not taken. Anyway, we've taken 8,650 divided by 2. We got 4,325. That is some poor maths. Okay. On plan, that's how far this needs to travel. 4,325. Okay. What is this here? Well, it is 4,325 times 1.305. 4,325 1.305, which gives us, I'm going to take a shortcut to tell you from here that it will give us this answer here. Okay? 5.644. Or 5,644 millimeters on slope. So we've got a 1 unit, our factor, we apply the factor to the span on plan, and then you get your distance of your rafter. That doesn't tell us this length for our hip rafter. So it's a bit easier from here, which turns out is just some Pythagoras. If you're taking, and it's interesting, I had to wrap my head around this. You've gone, firstly, you've gone from plan, a square, okay? You applied a factor to tilt this square up to an angle. So first you had a flat square, you've tilted it up, so it faces the ridge. At this end of your square is now on the ridge, okay? And it says here. But you only want half, you want that dissecting line through your square. And so you apply Pythagoras. Where are our numbers now? On slope, 4,325. And what's not given, but you can see intuitively, is if you've taken a perfect square, which we can, because this is at a 45 degree, this was 4,325, this is 4,325, so we've applied only one side of the square, right? It's 4325. What have I done? Right. Doesn't look great because I put that in the wrong place. So the 4325 is actually a better indicator if I put it there, right? 4325. And this slope bit is 5, 6, 4, 4. And Pythagoras tells us 4 squared plus 6, 4, 4 squared will give you that valley rafter length. Okay? And we'll make some further assumptions that because this is a perfect 45 and this is a perfect 45, they are both going to be this value. Okay? Both of them will be that value. So we will apply it by 4, which is exactly what has been done here. 4 times, and here's our Pythagoras, 5.644, 4.325, 5.644, 4, can't see it very well, but it is there, trust me. And you put it in there, times it by 4, and that is that. It's a tricky section. That is probably the most complicated to get your head around, because you have to visualize that we're first dealing with a square on plan. Okay? Now, we use this gable end, but there's obviously no rafter here. First dealing with the square on plan. You can't do much with the square on plan. You've got to sort of convert it to a value that sort of accounts for the slope. And if you were lazy, you'd not account for the slope and you'd just do Pythagoras straight. It wouldn't be correct. That might be a measure, actually, of a tie beam. If there was a tie beam that ran from the corner to the center, you would just take Pythagoras of the square to get this bisecting line. That would be a tie beam. But for in the case of rafters, you'd need to account for the slope. You find your factor to get your slope so that this whole edge is raised now. You've got to visualize it. Flat square, these ends stay flat. Flat and flat. Okay? This end is now raised. And by what factor? Well, you have to use trig to find how much this face elevates. Let's go. Jack rafters. Okay, the jack rafters, thank goodness there's less maths involved here, really. This division by 5 works, and I think it works in every scenario, regardless of what this angle is. We have a 45-degree angle at the moment, so, and I think it might apply to all angles, but I'm not sure. This one is a 1/5 length of this. What would be easier is if I actually do it on this side, because you can see it better. So that is 1/5. I'm just going to put a multiplier of 5. Then it's 2/5, 3/5, 4/5. Okay. And this is 5/5. So what we're saying is, of a given value, from there to there, our jack rafters appear to be dividing that value in perfect intervals. And since there are 5 jack rafters, we will say that interval is 1/5. So the length is increasing by 1/5 of the total. The total is 5743. That 5743. So we're not dealing with in plan in this case, obviously. 5743 does not come from plan. We are dealing with rafters, so we have to consider it unsloped. So 5743 is here. 5743 is our rafter. Now, funny enough, we're going to take the rafter value. We didn't do it previously. We're going to use it now. 5743, and it's in intervals. So what that's saying is, as we travel across this green line up the slope of the roof, this piece is 1/5 of that one. This piece here is 2/5 of this longer red line, right? This one is 3/5 of the longer one. And here we have 4/5. And the last one, obviously, because you can see clearly that we've now reached the full length. So 5/5, or 1/2, is not actually applicable. So once you get to 5/5, you should be aware that you've now reached the full length and is no longer considered jack rafter, right? So you should never reach 5/5. This is your maximum. 4/5. It makes sense. It should be, it's fairly logical. Okay, first category, not exceeding 2.4. So what's happened here is you've taken your 5743, which is given, and you're going to apply intervals of 1/5. So what I do is 5. Oh man, where did I try? Let's go across. 5743 divided by 5 gives you x. X is this smallest multiplier. And all you do is go 1 times the smallest multiplier. Gives you that one. 2 times the smallest multiplier. Gives you that one. 3 times the smallest multiplier. That one. 4 times the smallest multiplier. That one. Done. Easy peasy. 5 times 5, we ignore. Well, we don't ignore it. It doesn't apply. Because it's no longer jack rafter. So that is those ones covered. I've basically covered these as well. You've 3 times 5, like I said, you just take your smallest multiplier, 1/5, times it by 3, and you get this. And it might be worth noting where they're going to go, so let me just go back to that. But here we have example, 4 times your smallest multiplier, 1/5, give you that, and you put it in there. They're all jack rafters. Okay, well, we'll get to this one. Okay, let's take a look at 4 times 2. Okay, so for this plan, we have the following places where jack rafters, and we're lucky enough for it to be indicated to us in color on the plan as orange. I wonder. Okay, it's orange and black. I think this might be a bit misleading, and I'll tell you why now. Come on, guys. So you will see that this says valley rafter and jack rafters. It's orange. Here's your valley. Okay. Here's your jack rafters. But what this really means to say is jack rafters for this valley rafter. Okay. It is not all jack rafters. It is jack rafters for this valley rafter and this valley rafter at this intersection. So whenever there's a valley rafter, the jack rafters for the valley rafter are orange. This one is in black on plan for hip rafters and jack rafters. Okay. So that means we've got orange over here. And remember previously we said this one's a full truss. So we're going to just erase that. Drawing in 1, 2, 3, 4. From that side. 1, 2, 3, 4. Uh-oh. What I did was I ended up counting what would be the ridge on this side. So 1, 2, 3, 4. It's better. Okay. And if I count on this side, maybe I should go from the center again. 2, 3, 4. And we do not count the ridge, which we did previously. 1, 2, 3, 4. Okay. So you can see where the 4 is starting to come in. But where's the 2? So the 2 is on this side. 1, 2, 3, 4. So for this square, I hope this is going to be clear enough. 4 on this side, 4 on this side. Okay? 4 on this side, 4 on this side. For this section alone, we already see that there's 2 times 4. Okay? Let's jump across to our hip rafters. 1, 2, 3, 4. So I'm counting again. 4 and 4. Okay. And 4 and 4. Same story. 2 and 4. Now, I've made this process longer than it needs to be. As you get better at these things, you should just see clearly that there must be 2. There must be 2 for every valley or hip rafter. I'm trying to think of a scenario where there isn't 2. Let's see. Where would it not be? Well, I would say that on plan, you can see that this is pretty symmetrical, and this is a perfect 45 degree. Okay. And that's what allows us to say that there's 2. Here's 2. Here's 2. There's another 2. Okay, that's the longer one. Another 2. Another 2. So, because of the 45 degree in symmetry, we're allowed to say that this is, where are we now? 4 times. What I would have actually done is the other way around. I would have said 2 by 4. There are 2, so we're taking a smaller component, i.e. the individual dimension of the smallest one, let's say 1/5, 1.3, 1.13, sorry. Okay? We're saying there are 2 per square on plan. And we're saying there are 4 squares. Right? So, it makes a lot more sense to me, at least, to say 4 by 2 by 1.13. Okay, this is done the other way around, not a big deal. I think we've adequately covered that section. Hoop iron roof ties. It is the same story as the half trusses, right? The roof ties only fixed to brickwork and timber, so you have to take a look on plan and say, well, it's a jack rafter, so it's sort of floating in the air, not floating, but it doesn't have the same structure as a full truss. It's by itself, slightly unsupported, and it's going to sort of piggyback onto other structural members. So our jack rafter, that's it. That's our drawing. We've got our walls, and it's going to be fixed with hoop iron, and we're not going to describe how it fixes to the rest of the roof structure. So we do not elaborate on how it fixes to this rafter, the hip rafter. We don't expand on how it fixes to the valley rafter. Other places, like here we have an interesting scenario. This is a jack rafter that doesn't fix to brickwork or well, fixed to the rafter, but we're not going to describe it because of this. It's not covered. And it fixes in the air there. Now, we'll have to take a look at how that's described, because I don't think we cover it in the course. Okay, let's erase all of that. So, considering group 1, and intersects where jack rafter meets a wall. That's it. There are 4 on that side. There are another 4 on this side. 4 on this side. Another 4 on this side. Okay? In this area, the way I would probably describe it is 4 by 4. Okay? By 1, of course. Take a look. Interesting. Okay. Okay, so that. What? Okay, so remember to exclude that, which I have done. Do not count that again. That was counted during our half truss measurement. And let's just take a look at the jack rafters and places where they will meet brickwork. Now remember we said that this was a full one. And this one's also a full one. So is that one. Despite it looking smaller on plan, we've considered them as full trusses. So let's just make it full truss. Okay. Now the other jack rafters that we've accounted for are all floating. In my mind, they do not meet brickwork. They are in the air, either suspended by our valley rafter or are soon to be ridge beam. So, and in this case, is another ridge beam, right? So there are no, there's no hoop height on that side, only here. So I would just take that description personally, which is surprising to me because, okay, so what I've left out here in this description. So there, the description has taken the whole, well, not the whole, they've taken half. So they've said this is 0 4 by 4, they said that's 8, and that's 8. Okay, that's fine, I'll accept that. This one is because they have grouped hip and valley rafters as well. So there's our 2 valley rafters. Here's our hip rafter, 1, 2, 3, 4, and it has gone into our description or measurement. I'm happy with that. We can move on. Okay, so we're going to move on to the ridge beam bracing gang boarding. So ridge beam is sort of a, I guess, a conceptual thing that you need to grasp because it involves visualization, which is not so easy when you just have a plan in front of you. So what I did previously, I think I described what is actually going on here with a couple of these jack rafters, is that these guys are sort of floating in the air. They are suspended, and okay, these arrows are really messy. Suspended in the air, and you have to decide how would they be reasonably held. Now, a little secret I picked up is that this green line here, for our purposes, right, is ridge. Okay. Now, a ridge is just an area. It's sort of a descriptive word. It's not saying there's anything there. And in fact, in our case, there is nothing there. This is a sort of, it's like a center line. It's telling us that this is not a flat roof. Okay? It's telling us that this and this meet. And if you want to argue, you could say, well, it could meet down or it could meet up. It could meet like that, it could meet like that, okay? All we know is 40 degrees, okay? Because we're looking at a house and it's a roof, we know it meets up. Please, let's not get argumentative about these things. That means ridge, that's all it means. But, until we get to here, and we start saying, how are these jack rafters supported? And if you weren't aware of it, you would say, well, there's a green line there, it's fine. They are supported. That green line is nothing physical other than an apex, or telling us that this is the shape of the roof. That's what that green line is. There is nothing supporting them. You have to account for it, and you call it a ridge beam. Okay? And we're lucky enough to have a bit of a dimension there. We'll see how that calculation is done. So that ridge beam goes there. There are 2 ridge beams, by the way. There's one there, and there's one there. That is to support the jack rafters that we've previously measured that meet with a full valley rafter over here, right? That is obvious enough. Alrighty, let's cross over and see what we've got. First thing is a ridge beam main. Okay, you notice the use of the word main. First, for your next one, the extension. And just by looking at this one's longer, this one's shorter. I would say that this one is main, this one will be shorter, so we'll say this one's the extension. Okay? And how do we get to that calculation? So this is sort of applying neat little division by virtue of having lines and trusses, and then meeting up and, you know, making things very convenient for us. So we count how many divisions there are within this 26.5, okay? How many divisions? And I'm not going to count it because I'm lazy, so I'm going to tell you that there are 33 divisions in this 26.5, and that comes to 803. So what we are actually saying, and I'm going to take a look now, but it is speaking to the center-to-center span of each truss, let's take a look. If it's given, it's not. No. Okay, so what you've essentially calculated is the span from one truss to the other, and since we're saying it's actually inside to inside, is 803. So center to center, if you wanted to calculate center to center, would actually be possible. The inside of your trusses is 803, and you know that the timber used in your trusses is 38 by 152 for your tie beam. Let's just take that for example, 38. We'll say this one's 38, this one's 38. So essentially, if in theory you wanted your center to center value, you'd take 803 and you'd take half 38 and half 38, basically plus 38, right? And that is your center to center value, which we're not going to use at the moment, right? We are using 803 by virtue of our divisions made by the trusses. Okay? Alright. 33 trusses. Span between them is perfectly 803. How did we get here? So, you have to see ahead of time. Now you might have said, well, I want to take this value, 7,600, and I don't think I would have blamed you, because I might have done the same. But what the description is saying is that you should be careful, because here is an indication of where 7,600 is. It is along the walls, and that is not a good enough. It's not a good enough outline for where exactly is jack rafters. Where exactly do they meet? You can't take 706 and you can't work down from 8650, okay? You need to apply the rule and the divisions, because the divisions will give you a perfect exact value on how far this ridge beam needs to be. This one over here, this main ridge beam. So this main one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we'll say it's 10 times division span per truss. Well, let's take a look here quick before I write something. Yeah, that is exactly what's happened, okay? That is exactly the distance of this main ridge beam, and the extension is 1, 2, 3, 4. And I wanted to say 4, but it's actually 5, and I'll tell you now why. Let's take a look. There we go, it's 5. This touches on another little bit of a complicated thing here, is that your ridge beam cannot stop on your last jack rafters. It needs to go one span further. And this will become quite obvious to you now. Your jack rafters are here. So if you say 8 times 803, you are putting a ridge beam there. And basically what you've done now, in theory, is you fixed a whole bunch of jack rafters to each other, but you have not fixed that system to the full trusses. So if you've applied 803 by 8, in this case my drawing, 803 by 4, 1, 2, 3, sorry, by 3, it's just going to collapse. Okay, you've got to go 2 further to fix this system to your full trusses. Okay, and that's what's happened. So do not count the pink lines. Well, maybe 1, 2, 3, 4, 5, 6, 7, 8, 9. See, so pink lines will give you the units, but it's not a reflection of the spans. So count the spans and be careful. Make sure it makes sense to you. And the same applies here. Like I said, our eye actually almost said 1, 2, 3, 4, and would have just been floating and collapsed. Right? You must go 5. You must go one step further to fix the whole system to the rest of the roof, so that it is actually supported and makes sense. Okay. And I think it's important to make sense of measurements, because it makes it easier. It definitely makes it easier. What did we say here? We did the 8, we did the extension, which was 5. Okay. The bracing is exactly the same measurement as the hip rafter. Where is the hip rafter? 7.11. So if you go up and you look at our previous calculation for hip rafters was 7.11. We've taken the exact same thing. We're basically saying it runs parallel. And the person who was describing this drawing decided that we'll have 2, which is obvious. 1, 2. And they also decided they want 3 of these systems, bracing structures. So we erase. And, oh my word. What do we say? It runs parallel. Oh my goodness, that's not good. What do I could undo? Okay, just try again. Parallel. Parallel. Okay, obviously they should probably meet at a corner so that ends can be fixed nicely. Because remember, there's no actual wood along this ridge. Like I described, it is only for our ridge beams that there's timber. Anyway, the description decided to put 1, 2, 1, 2, 1, 2. Okay? Basically, 2, sorry, 3. And this was 7.11. Right? Let's take a look. There we go. Jack or value, hip or value rafters, basically rafter length. Since it's parallel, you take that exact value. There are 2 per sort of triangle shape, and the last value of 3 is up to you to decide. If you want to say they are, I don't know, 6, you can change that to 6, and no one is going to argue with you. You are just very, very thorough builder, and you want to make sure your trusses do not distort. I don't know. Okay, so what is that now? Gang boarding is another pretty straightforward. Well, let me backtrack a bit. The 1 is straightforward. Okay, 26.5. You've got a piece that runs that way. Maybe I should just rub this out before we start. Okay. So let's make this nice. Obvious. 26.5. You want whoever enters the crawl space to be able to walk the entire length of 26.5, and you. Let's just take a look real quick. 6 minus the wall length. Okay, so what happened here is we want to know where. Come on. Where exactly is this point? Let's take some now. Where is this point? Okay, because we're not going to put anything here, but we do want to extend a little bit of walkway that way, obviously. So maybe you have a geyser over here, and maybe a second geyser over here, and I don't know, an attic. So how are we going to extend this direction? We need to know a starting point. So they have, what's happened in the description is you've taken, it's not so obvious immediately what is going on here, but you've taken that wall-to-wall span, you've deducted the values of the wall, the thicknesses of the wall, since the cavity wall is 110, 50 and 110, right? There's your value, 7,060. And you say, well, why do I need 7,060? And it's because you want to know where your starting point is from your. So it's better that you put your gang boarding in the center. Okay, let's not go into other scenarios where you put your gang boarding here. It doesn't really make much sense. So the gang boarding goes in the center, and because it's in the center, you can take a value for the inner dimension and divide it by 2. Okay, and you get what halfway is. And the halfway, this halfway measurement means that from the center line to, well, the edge of the brickwork, so you have to excuse my drawing here, to the, the edge of the brickwork, and remember, it's the center, the inside face of the brickwork, that is this value here. Okay, so we've made progress. Let's draw it in, make it a bit thicker. We've come this far. Remember, inside face, okay? So since we've come to the inside face, what else can we steal from the drawing to give us more information on what's going on here? Well, this again is not so obvious. 10,900 will take you to the edge of the roofing, but it doesn't take you to the inside face of this brick. So you have to make some assumptions again. 525 is our eaves distance on flat. Okay, we are going to assume there's also 525 that way, right? Okay, here's 525 as well. 525 that way. Now I'll do the full calculation to show you that you could actually take this value straight, and that's what happened. But let's take it further so you can see. We want to move this 10,9, 525 that way, and then 525 again inside. So we're moving it 525 twice. So what would happen mathematically is you'd subtract 525, and then you just add this 25. Sorry, 525. And at the end of the day, you'd end up with an add and a minus, cancel out, and give you 10,900. And that is exactly what we have there. It is taken straight because the person describing this measurement could see, without having to do any calculation, that you could just take this 10,900 with the assumption that's 525, and that's given 525. If you shift this 10,900, you shifted 525 that way, and you shifted another 525 this way, you will be left with the same value, okay? And let's draw it in just to show you what we've calculated. It's going to go from the inside face, and it's actually, I think, a bit too long. I'll just tell you why now. We have gone right into the hip, and I guess it's okay, there's nothing wrong with it, and possibly should connect with the wall plate. But this space isn't very easily accessible, is it? Basically what we're talking about is a kind of space that's this size towards the end. But this is how it's calculated. Gangboarding. The 26.5, 14.43. So what happened there? You took it straight. Then you took what you needed to do was find half, this is half of the inside span. Alright. Okay. Let's do some cleaning up again. Come across to a drawing. That page is done. Thank goodness. Roof coverings. There's a huge description here that you must memorize. I will just point out that we've taken, this was our multiplying factor to go from flat to sloped. Now we do that a lot. If 1 is here, that's 40 degrees. What is x? And that's just cos. And some basic tricks. So we will leave that. We will go over how this measurement was calculated. 26.5, 8.65, 10.9, and 8.65. There's our 26.5. And what I want to point out to you, probably the most important thing, is that you do not have to calculate the actual roof covering area. That this right here is a magic number that turns anything on flat into sloped, and it is a shortcut. So as soon as that goes in, you are saying that whatever you put in here must be sloped. It has to be, because you've used a multiplier. If you put sloped in here and sloped there, you've made a big mistake. So 26.5, here's your 8.65. So we're saying that this entire square coverage is done. 26.5, 8.65 covers this on flat, and 10.9 by 8.65 will get us this last bit, right, on flat. And because of the multiplier, we say thank you very much for saving us the time and suffering of not having to actually do it. And you might say, well, I don't think that's right, because it's not a sloped roof or a purely sloped roof. You know, there's this part, and this is not really perfectly sloped. If you can visualize this, this is a valley, so it's not perfectly sloped as a monopitch roof would be. That's perfectly sloped, so you can see quite clearly it's 1.31 applies to this whole area, and that makes sense, and it makes sense to me too. And this part here isn't so obvious. This is tricky, and the same here. So, well, how can we just straight apply this factor, and somehow it gives us sloped values? And it is a bit of witchcraft, I guess, but it does work. Let's just investigate this a bit further. So, okay. So what I wanted to do was to actually turn these. Let's start with this side. Okay. We're saying, because it's 45, what you can do is we've basically taken a corner and we've cut it, right? You've taken a perfectly sloped corner and you've cut it. And then you've rearranged each half so that it's, instead of this center line lining up, actually it does line up on this example too, but you're rearranging it so that instead of, so this half is running upwards on this side, you've cut it in half, you've taken this other half and you've rearranged it. Oh man, this is really tricky to visualize, I must admit. But instead of it being, this section being on the higher edge of the slope, you're saying that it's starting down here. There we go. Now it's making sense to me. Okay. Instead of saying that this is in the air, it's now on the ground. Well, not on the ground, it's on the same starting point. Here. Okay? And instead of this piece, hold on, we're getting there. This piece is sloping. Okay. I'm going to have to spend some time figuring this out to actually, you know, make logical sense of it, because I know it works. I'm struggling to understand how it works. But I would say, for now, is to assume that because it's a square and it's on slope, it is the same as a square on slope, okay? This is the same as that, provided that their on-plan dimensions are the same on the sides, okay? Then it's the same square. I do not have the proof for you. Not yet, at least. You're going to have to give me time to figure that one out. We work with the ridges now. So, let's just say that's ridges. What's interesting here, what I've picked up, is that it is ridges, but it's specific to what we call what was previously the ridge beam. If you recall me explaining the green line, there's nothing there. Okay, it's the ridge. This green line is the ridge. The only place that there's actually something is where we put ridge B. Anyway, what we're saying here is we're putting a ridge all along that green line. All these tiles, they're lapped nicely, so they're nicely waterproofed. Water comes, runs down, it hits here, it runs down, hits here, it runs down. But if it hits the center and we haven't placed anything, it is going to enter the roof. So what a ridge tile is basically a little cap to ensure that if water happens to land in the center, and we can assume that because it's rain, it will land in the center and won't decide not to, it's going to hit the ridge tile, run off, and because all the tiles are lapped nicely, let's go down here, there we go, bounce, run down, bounce, run down. Everything is nicely lapped. There is absolutely no way for it to return under a tile. Well, I wouldn't say absolutely no way, there might be. I can't come up with the reasons why, but there might be. So, I said it's along the green line. Let's go back up here and take a look. Oh, come on. Green line. So we're taking the 26.5. This is, I want to say it's the same as the gang boarding. No, the gang boarding went all the way that way. Plus that, the gang boarding is too long. So what it is, just took the 10.9 straight. And I'm not sure I'm happy with that. Let's just take a look quickly. Register tiles. Hips of tiles. I don't know if this 10.9. Okay, well, there's the answer. Not so obvious because I drew a big line. Okay, it does make sense. Yeah, I'll tell you why. We've done the same thing as we did previously. We've tried to make sense of areas where there's no dimensions. So we make certain assumptions. We want this. We want this. Okay? And we know that this is a 45. And so this is a perfect square. Right? That is a perfect square. Which means that this is x and this is x. Okay. And we've previously done the calculation, and I'm going to have to check. But I'm going to say that it's the same as this. It's the same as this square here. Okay? It's exactly the same. Also, x and x. So if we say that 10,900 moved x this way from that line, moved x this way to get to this point, 10,900. What? How far does, so we moved x that way. It's still 10,900. And you want to know, does that reach this point here? And the answer is yes. And why? This x, and sorry, that x are exactly the same. And they're exactly the same because it's a 45, it's going to intersect halfway with this width. Right? And because it's halfway, and this ridge, which is not a ridge, it's just a ridge in inverted commas, apex, is also in the center line where you say that and that is the same. And because we moved by x this way, it must move by x that way, and we can take 10.9 as it is, and we multiply it. Sorry, not multiply it, add it in linear meters of ridge tile. Okay? Hips. The hips, that is, I can see that is straight from the ridge. Sorry, that is a hip rafter value. Okay? And there are two hip rafters. 1, 2. Okay? Let's take a look. Okay, the valleys. Valleys are unique in the sense that they do not get a tile. So the tiles, oh, that looks terrible. The tiles, let's just assume that this drawing is part of a valley. And you have, oh, I've left my tiles the wrong way. Okay, this is the valley. We've got a whole bunch of tiles, and they all meet in this valley. Right? Oh my goodness, it's not getting any better, is it? They all meet in the valley. We've got a ridge tile, it's this shaped. Now, you might say, why don't you put a ridge tile like this? And it is unnecessary because what you do is rather put a thin sheet of steel. The description specifically is galvanized sheet steel lining. Okay? Thin piece of steel that runs along. Okay, so they obviously have to fix it early and then lap the tiles over it. Okay? This terrible drawing. And so when the water runs down, it bounces and it goes past the last tile actually into a little steel, let's call it valley lining, and then after that it runs along the lining and out. Okay? In our case, let's just take a look. Valley go to elsewhere. So it bounces in that valley, which happens to be right over here. Any water that lands there, or here, or here, or here, or here, is most likely running down the tiles, bouncing, and running into this gutter, into the corner angle, gutter angle. Bounce, runs down into that gutter angle. And take a look just now, there might be an outlet there, I'm not sure. I have to look quite carefully to see the outlets. It's not indicated that there's an outlet there. So it would bounce, run in this valley lining, hit the gutter, and then it would decide which way it wants to go. Does it want to go down here? Or maybe it wants to go down there? It's not picky. Choose to go down here or down there, who knows? And that is your valley lining. If that is not there, this whole section is just going to allow water into the roof. Okay? Nothing is stopping that water from running down the tiles and going straight into the roof. Okay. So, happy we prevented water from entering the roof through the valley. Great news. Okay. What the hell is this? That is our intersection tile. Okay, it's fairly unique because you have this huge roofing system and you have to look carefully where you need an intersection tile. And not all intersections need an intersection tile. How do you decide where they go? There's only one. And the script description says to intersection between ridge and hips, which is good news for us because at least I can try and understand where it's going between ridges and hips. Okay. Yes. That is it. That is it. Between ridge and two hips. Okay. That is our intersection. So you might say that you should put one here. And let's just try and dissect why we don't put one there. And let's firstly make sure, is it on description? No, there's only one. And it is ridge and hip intersection, which is that one. This, so what I would say is we look at the differences. This is a hip rafter and it's raised. And this is a valley rafter and it's depressed. So I would say the discerning factor in deciding where this custom piece goes is where there are more raised pieces. Let's just draw it in, so it makes sense. Sort of a T shape, Y shape. More raised pieces than this side, which in fact there's no raised piece here. Okay, so there's your first problem. Is what you might want to do is put a piece like this. But I would say that this valley rafter is not really accounted for with your T intersect like that. It just doesn't fit nicely. I'm not sure if there is a piece and purpose-made tile for that. There probably is. It's just not accounted for in this description. What I want to say is just assume if there's a nice intersection at 1, 2, and 3 sort of raised ridges, we will put a purpose-made intersection tile. If there's 1, 2, 3 but depressed intersections meeting it, exclude a purpose-made tile. Maybe it's something else that goes there. I cannot tell you. Let's move on to tilting fillets. Spade tilting fillets is pretty self-explanatory. They're taken 26.5 again. They're taken 10.9. They say, well, this is 26.5 straight there, and this is also 26.5. Here's 10.9. Oh, did it again. Apologies. 10.9, 10.9. And what's important to note is the gable ends do not have splayed tilting fillets. It is only where the bottom of our slope starts to meet the edge of our rafter. That is where you need to put a splayed tilting fillet. And if you've been following, the purpose of a splayed tilting fillet, or just a tilting fillet, is to account for the fact that every tile rests on another tile from the top all the way down until you get to the end. And guess what? Last one is not resting on the tile. Very sad indeed. So we need to help it out. And what happens here is this pattern might be 38 by 50. But this one needs to be taller, right? 50 by 50. Because all along here we have intersections where tile comes in underneath. Sorry, another mistake. Tile, the bottom tile is underneath. Tile comes in on top. Okay? And this little extra bit here props it up. By how much? Well, it props it up by the thickness of the tile underneath it. Pretty clear. So let's say the tile is 25 mils thick. Maybe that's a bit too thick. Anyway, that's fine. 25 mils thick until it gets to this poor little end bit, and it's not propped up by anything, guys. So in order to account for this tile's thickness, all along here is resting on a tile. All of it, except this one. We need to either increase the size of our patterns. In this case, we have a 50 by 38 turning into a 50 by 50. You could go from it's a bit tricky. You could go to a 50 by 76 if I recall correctly. You could also, don't take my word for it, but you could change the orientation. So instead of 38 by 50, you could go 38 by 50. You just change the rotation, the orientation. So let's just take a look at how it's done in the description here. So the description is 50 by 50, and over here it was 50 by 38. So you see that we upgraded. It's an entirely new piece of timber. It didn't do the trick that I'm saying, where you just put it, instead of 50 by 38, it's now 38 by 50. It's the same piece of timber, just different orientation. We upgraded it to 50 by 50, and that is the end of the description. There's not much more to say. Let's go here. Okay. Flashings apply where we have roofing meeting brickwork. All right. That's typically gable end. And I need to correct myself. Not necessarily just a gable end. It is a gable end with a parapet wall, because you can have a gable end with a barge wall, and in that case you would not have flashing, right? Right, or wrong. Correct me if I'm wrong. So, these areas are raised. Okay, they come above the roofing. The roofing does not extend over. Had the roofing extended over the brickwork, it would simply be a barge board meeting your fascia boards on the ends, or some other orientation combination. But that is the extent of where you're going to see flashing. And let's just break it down. What exactly is flashing? Well, you have your brickwork, and you will see this if you take a look at brickwork that meets roofing. It's quite clear why it is called flashing as well. It is bright, flashy steel, or let's just take a look here. Galvanized sheet steel. And the interface wear roof, let's just say this is a mono-pitch roof to make my drawing easier. And it's not great, but it's sometimes stepped, and you will see it in public as a step flashing. Well, I guess stepped like that, it needs to be parallel with earth, so stepped, it runs down, right? And you need a cover flashing. So there's two things going on here, flashing and a cover flashing. I cannot give you specifics, but I will say this much. It is a similar concept to roof tiling. You have one thing on top and another thing underneath, and it gives you lapping. And based on the science of lapping, you have created a waterproof surface, because if anything hits here, it's going to run down, and it's not going to decide to defy the laws of physics and travel up. Although, like I said previously, maybe there are scenarios where it does happen, I do not know. Flashing and cover flashing. Cover, and I think it's like this. Cover, F, cover for flashing. Okay, and this is just flashing. Okay, flashing and cover flashing, that is it. That is how this applies to the drawing. We have a brickwork meets roofing, okay? And what happens here is it's taken, let's just take a look at the dimension, 7.60, 7.60. It is taken, and what's convenient about that dimension is that it goes right up to the edge of the brickwork, and again right up to the edge of the brickwork. So you can take that. It's very important you apply your multiplier to go from plan to sloped. So from plan to slope like this is simply 1.31. Okay, happy? Good. Ease of edges, and 2. This again is straight from the drawing values. What I would say is important here is to take a look at 0.50. This is your calculation, it's just a perimeter calculation based on this, right? 20 on the top, you've got to go 230 for the sides of your boards, fascia boards in this case, another 230, and another 20. There's your proof of how much coverage you're going to need for all these boards. And you apply this factor here so that you can simply give a linear dimension. And because of this factor, it'll give you your square meters of coverage. Okay, water-shaped timbers. Let's take a look. 34 times 2, you can see immediately that would be your full trusses, because there are 34 full trusses, right? There are 10 half trusses. So what this means, and I'll do the math now, so let's see there. Unless it's given. Let's take a look. There we go. So what they've done is it's given that the shaped ends are 780 mils long. What they're saying is that our trusses can be, we can sort of ignore the aesthetic quality of the truss members. But as soon as you get to this edge onwards, we want 780 mils of wrought and shaped, and I think it's going to come that we also want it treated nicely, and we do. It's going to come. It's over here. So I'm going to just foreshadow that it's coming there. We're saying that this timber is not too important what it looks like. It can be sawn. Over here, we're going to specify we want it shaped. So shaped means basically a normal piece of timber would have been square, right? That face would be square with the length, and so with this face. All we're saying is carpenter is going to spend some time and cut a nice angle there. I don't know what angle he's going to cut. He's going to cut this piece off and throw it away. And the same for the other side. Okay. Now that's given as the total length after the brickwork. Basically the eave on slope. Okay. Here's the number: 2 for full trusses, 1 for half trusses, and they've also accounted for jack rafters, which are these ones. Let's take a look. 8, another 8. We don't include these jack rafters because they're floating and not exposed, so 2 times 8. We're happy with that. This is an interesting one, and it takes a bit of math. Okay. What has happened here is similar to the previous calculation. What you want to do is you're taking a very small square. A square similar to what you previously looked at, right? So we previously looked at a square this size because we wanted hip rafter. What we want to do now is we actually want to account for the ends of the hip rafter, which follow a similar pattern to the hip rafter itself. Here's the end, and we're going to say that this 525, let's take a look, maybe it's down here, let's check. Yes, 525 is there, and when it meets at a corner, it is going to be like this: 525 there, and 525 on the side. 45 degree, we make assumptions. The only assumption here, of course, is that this is 525, because it's a 45. If this was not a 45 and it came in like at that angle, well, there's no knowing. You'd have to do some more maths to figure that one out. Anyway, we do the same pattern. We say, well, what is this slope? Because remember, this 525 is sitting flat. This 525 is on the slope, though, okay? So, and this 525, flat again, because it runs along the gutter. So, flat on this face, flat on this face, and so we can apply it to our little square. But what is this face on the slope? It's 525 times our previously given factor, not 1.31, correct? There we go, 305. And you should probably, in fact definitely, take the exact value and not the rounded value, because you are going to end up introducing errors, rounding errors. 525 times 1.305, you will get 685, okay? That is just 525 on slope. That tells us it's 525 on flat, travels 685 on slope. Okay? 685. Now we can get this. Now we go across to the triangle method. Break it up into the triangle now. 525, 685. What is this? Y. And this is simply Pythagoras. Square, 525 square. And you should get 863. There we go. That's what I've just done. Okay. 863 is the length this rafter in the length of the hip rafter that is exposed after the brickwork. It's important to remember that it is not the same as this length, 525. It's a bit longer because of Pythagoras. Okay. So that I'm happy with. You should be 2 because the only thing I have not explained, 2 by 2. Let's take a look at 2 by 2. Why have we done 2 by? Well, 1, 2, 3, 4. Yes, that is where that comes in. There are 2 on each side. 2 here and 2 on this. 2 hips and 2 valleys. Well, 2 for the hips and 2 for the valleys. Wall face on sawn timbers. This is just a value of all the exposed sort of what we call it, supportive members of your tiles. And I don't mean trusses. We have smaller battens now running across like this. Sorry, they're going to meet there at that 45 and change direction, right? So what we want to know is which pieces of timber will be visible to the world, and how do we treat this timber. If you are lazy, you might leave it and say there's nothing wrong with it. No one's going to see it, I don't mind, maybe there's bushes and trees here, who knows. But in this case, and I think for most cases, we will assume that you want it wrought. Exposed eaves, basically, because, well, that's what this assumption is. So maybe I should check in the spec, and maybe it explains to us. a bit more about why we were making these wrought. Too bad, eaves. There's our explanation. So, because the spec says so, okay, we can assume that these are exposed eaves. Okay? You can assume that because these people are worried about the appearance, the visual aesthetic appearance, and if that was not the case, if this was not here, you'd say, well, it's probably closed eaves, and in quantifying that, I'm not going to put anything, I'm not going to measure anything extra for these exposed eaves. Covered eaves, closed eaves, because there will be a piece covering that timber, and no one would even know what the timber looks like. In this case, wrought, it's exposed. It's a simple perimeter dimension of each piece of timber, right? That one is a 50 by 50, because it's obviously 4 by 50, it's 50 by 50. And this one goes together, I would say that's a 50 by 38. And just from our previous work, I'd say this one is a tilting fillet, right? And this one is just normal. What is the pattern? Okay. Tilting because it's taller. Great. Okay, now you take these perimeters, you apply them here, and you'd say, the first thing, you'd say, well, why two? What is it? Tilting fillet on the end, and a batten. So how must I know that there's a tilting fillet and a batten that fits just in there? How do I know that? Well, let's just take a look quickly. There, and there. That is a clue. That within this 525, the span is enough, or small enough, to allow two pieces in there, okay? If this span was longer, let's say it was double, you would only fit the tilting fillet, okay? If the span was halved, you would put 4, okay? So 1 tilting fillet and 4 battens. Very unlikely that would happen. I don't think it does happen. It would be very uneconomical. So, tilting fillet, batten, all along your surfaces except for gable ends, okay? And that is what happened here. And I foreshadowed this a bit when I said, why do we want this wrought and shaped? Well, it's likely an exposed eave, and we will add to that fact. And say, well, it's exposed, maybe we want to paint it a bit, maybe varnish. Anyway, we are going to treat the exposed ends of all in all as part of the spec. This is the basic description, and what I want to explain is that's just the perimeter of a 76 by 114. That's pretty straightforward. So what are we saying? There are 2 of these shaped ends. That comes from, we change the color so it makes it more obvious. That comes from here. There are 2 of these shaped ends per truss, and there are 34 trusses. Okay? And so well, how do we get this? This is previously calculated. 780 was from there. Wasn't calculated, it was given from there. Okay? 10 for your half trusses, given. And this is your perimeter. Okay? Again, 780. These are your jack rafters. Okay? 8 times 2, remember? 8 and 8. Come on. And 2 by 2. A little bit less obvious. Let's take a look where these 2 by 2s are going. 1, 2, there. Okay. This, which we've already calculated, right? 860, yeah. These are the 860 mil ends. These are the ones that needed this calculation. Down here, the magic trick of the square and then the triangle. Okay, it's 860 mil ends, and this section would be from here. Okay, so what we've done on this page is we basically said what is exposed. Okay, then I'd say how is it treated, or how is it finished? And that, just 2 questions, is a whole page of work. So, at last, rainwater removal. And I'll try and get this done a bit faster. So, something important to note here is that there are 3 dimensions, and when I first saw this, I thought, okay, it's not a circle, or a half round. You don't get circle gutters for obvious reasons. Half round is just 1 dimension, 125, right? So, this is a rectangle. And I would assume it's following this kind of pattern. Now, I'm not sure why 115 is repeated twice, because I think you could get away with just saying that, and people would know, just by thinking logically, it must, well, okay, you might say this is 125, and this is 125, and this is 115, so how would you know? Well, there is your reason why it's in twice 115. So I stand corrected. 115, 115, 125, there we go. It is a rectangular roof gutter. let's just take a look at 0.36. We are saying that with gutters, the inside face should be waterproofed. Let's make it in blue because we want to prevent the water that enters this gutter. We want to prevent it from causing any damage to the gutter itself. So we're taking the sum, and that comes to something around 0.36. I haven't done the math. There it is there. 0.36. It's 355, you round it up. This should be clear by now, is the length of the longest part of your house and the shorter faces and then this inner face. So 26 gets this full side. And there we go, the step piece as well. And then the divisions of 26 get all these faces. And then the 10.9, which is here, I've just drawn over it, we'll get these faces. Okay. Great. And you'll notice they also added the description for the, so this bituminous coating is on the inside, and this is on the exterior. And if you were sharp, you would say that they are not the same dimension, and I would probably agree with you. And some people might be saying, what the hell are you talking about? Well, 115, 125, 115 is the exterior, but the interior is actually quite a bit smaller, because you have to account for what thickness this is. This is a 10 mil, 1 centimeter thick. I don't think 1 centimeter thick is too unreasonable. If that's a 10 mil, then the inside will be shorter, come up by that much. So the inside, and what, 5 mils in, and 5 mils in, and 5 mils in. So the inside dimension should be smaller. By how much? Well, let's just say that it is negligible, so that we do not have to suffer through another calculation. Okay? We say it's the same. We do not care about the thickness. We say it is negligible. Please. Alright. We're getting somewhere. Stopped ends. Let's take a look at stopped ends. Stopped ends appear when we have... Oof, I can't even see anything on the board. Now, I want to be careful now. I don't want to tell you the wrong thing. The stopped ends, angles and gutters. So, what I want to explain quickly is that despite this gutter running that way, and running that way, that way, that way, despite it having an outlet, if you look carefully, there's a little solid blue dot there, and a solid blue dot there, and there's all solid blue dots. Despite it having an outlet, there's also an end to this, and it happens to be right at the outlet. In order to visualize it, let's say it's running this way, okay, and you have your outlet. I should be careful, what shape is this outlet? There's also, well, there, 500 diameter downpipe. There's a circular outlet, right? Sorry, did I say 500? 100 millimeter downpipe, okay, running down. And a stopped end. Alright, a stopped end. Otherwise, how is your water going to go down your downpipe? You kind of just launch the water off the end. And sure, some will go down. Some. And I think the majority in heavy rains will just rush straight past and hit the end. And thankfully, because we got the stopped end, I'm going to pull back and decide, hey, I want to go out the downpipe. And it's going. Alright, so it's not so clear, in my opinion, that a stopped end should go there. You have to visualize this kind of stuff. It's running down there, it hits the gutter, but the gutter is simply a hole in the bottom. Of, sorry, the downpipe is just a hole with a pipe fixed to it, but it doesn't force the water to change direction and go down. The only thing forcing it is this little magic stop end. Okay, I think that's enough on that topic. Stop end. Stopped end, not stop end. Stopped end. Okay, angles. Angle, very clear. 1, 2, 3, 4. That is pretty obvious. Okay. Now, if you look carefully, you'll see there's actually 6 gutters. You have to really look for it. I wonder if perhaps it's in the spec, because to me, it's something that could easily be overlooked if it's not in the spec. Let's take a look. Okay, it's not in the spec, so you have to look very carefully, guys. I'm going to draw in red. There, I spotted 2. 1. Yeah. Not so clear, but that is life. There are 6 outlets. Happy? Draw. Okay, downpipes. This is sometimes assumed. And 6 matches. Oh, that's 6 for the downpipes. Okay, you don't have, sorry, downpipe per outlet. You can't have an outlet and then water just sort of runs out the side of your gutter. You probably could do that. I don't think it's a good idea. And at the same time, you only coat the outside of your downpipe. And for the sake of completeness, you probably could coat the inside of your downpipe, but we do not cover it in the course. If you want to be creative, maybe you just pour bituminous paint down on your downpipe until it comes out the other end into another bucket, and then you let that dry and your downpipe is now bitumen coated on the inside. You know, that's pretty easy. I don't think it's really too difficult to pull that off. Anyway, you don't add bituminous paint, you just coat the outside as per spec. And finally, our last description is for our eaves, offset, and the shoe. Let's hop onto this picture here. And the way I'm going to describe it is that the gutter is like this, right? And if you have a downpipe, if you come down, it's going to make an angle. Okay? And of course, at this angle, so the water can still run. So it's at a slope, which is sort of a fundamental of plumbing, is that it must be sloped for water to run down. You definitely don't turn at a right angle and then down. It is sloped. And it's going to hit the wall and run down. And it's out to the wall with a couple of brackets. I don't see them in our spec, so we don't speak about the brackets at the moment. And then it gets to the shoe, which is a little like that. And that is it. One offset and one shoe. Well, firstly, let's just summarize this quickly. We have one outlet, which needs one down pipe. Okay, and that one down pipe needs one eaves offset and one shoe. Okay, so that should be in your mind when you get to a section called rainwater removal. And there are some other things to consider, like I said, the stopped end. And that brings us to the end of this measurement. I hope it has been helpful, and I will see you next time. Thank you for listening. I hope you enjoyed. I hope it was helpful.